Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 28, 2025, so just yesterday. This paper shows that a whole class of seemingly complex mathematical operations, known as generalized Legendre transforms, are actually just the standard version of that same transform applied to a specially modified function. The paper is titled, "A Note on the Artstein-Avidan-Milman's Generalized Legendre Transforms," and its conclusions offer a really elegant new perspective from the field of information geometry. Essentially, the work clarifies that these supposedly generalized transforms are just different geometric expressions of a single, fundamental operation. And the community on X is definitely picking up on that connection to information geometry. The main discussion online seems to be focused on this core finding, that these generalized transforms are equivalent to the ordinary Legendre transform, just applied to what are called affine-deformed functions. Essentially, functions that have been mathematically shifted, or scaled. People are highlighting this simplification, and especially the link to information geometry, which provides a much clearer, more intuitive framework for understanding these relationships. So, to really grasp that geometric connection, the authors provide this helpful figure. It shows a set of nested circles, each one representing a more specific class of mathematical function. The outermost circle is the most general, and as you move inward, the functions gain more structure, becoming what are called proper, lower semi-continuous convex functions, and then even smoother differentiable ones. What's key here is how each of these layers connects to different concepts in information geometry, like Hessian geometry. This diagram really sets the stage by illustrating the rich geometric world where these transforms live. To make that geometric world a bit more tangible, these plots show a concrete example. On top, we see a pair of what are called conjugate functions. They're essentially two functions linked together by the Legendre transform. Now the key detail is on the bottom. The function on the left has a sharp point, so it's not perfectly smooth. Its slope at that point is shown as a subgradient, which is a generalization of a slope for these kinds of functions. Instead of one value, it's a whole range of values, shown by that red line. And digging into the math behind those plots, this section gives the exact formulas. It defines the function f of theta, which has that sharp point we saw. Because it's not perfectly smooth, the authors define its subdifferential, which is the set of all possible slopes, or subgradients, at each point. And sure enough, at theta equals 0, the subdifferential is the entire interval from -1 to 1. This is the mathematical definition for that vertical red line we saw, representing the whole range of slopes at that single point. So all this mathematical machinery, from the subdifferentials to the specific function examples, really serves to build up the core argument. The key takeaway is that these so-called generalized Legendre transforms are not really a new class of operations. They are just the standard Legendre transform, but applied to functions that have been stretched and shifted through what's called an affine deformation. This insight elegantly simplifies a complex topic by reframing it through the lens of information geometry. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.